also ask questions and interact with the speaker in the hallway over there after the talk. If you want to tweet about this talk, please use the hashtag #PyconJP_. So we're just about to start. Viola de Sosa. And the title of the presentation is Tracking the Invisible, Geoinformatics and Human Social Behavior. Before the presentation, the speaker will read a statement out of the microphone test.
So this is the mic test. My name is Sosa-León. The title of my talk is Tracking the Invisible, Geoinformatics and Human Social Behavior. My presentation will be in English. The presentation materials are also in English. I will publish the presentation materials, and I agree to having my picture taken during my presentation. I will comply with the PyCon JP Code of Conduct.
So thank you very much. The presentation time is 30 minutes, and that will be followed by a 10-minute question and answer session. Please welcome Viola de Sosa.
So good afternoon, everyone. Welcome to PyCon's conference in Japan. As I already said, my talk is going to be called Tracking the Invisible, Geoinformatics and Human Behavior. As a first short introduction, I have been working as a software developer and a project manager in Latin America and Europe as well. I'm doing currently my PhD in Geoinformatics in Germany at the University of Münster, and I'm very happy to be here in Japan in the Human-Robot Interaction Laboratory at Kyoto University, working with Professor Takayuki Kanda. And most importantly, I would like to share with you my interest in integrating human behavior and integrating spatial cognition and computer science. So I believe that spatial science goes beyond geographic maps. Imagine that you are in a room, like we are here in this conference, and you're walking towards a door, towards the conference exhibition or something like that. When you do these kind of things, you're going to have what is called your body orientation, but also you're going to have a distance to other bodies, right? Or you are also going to have a focus of attention. Your head is going to be moving to one side of another. And we can physically detect that. We can see that in cameras, and your body will tell us about it. But there is also something called the socially occupied space. That space that is completely invisible. That space that you are conscious or subconsciously respecting to each other. So you know that you kind of cross someone's way when they are walking, or if someone is going to go or looking at something, they are going to cross that path. But that is something that you agree on and that you want to respect. But those constraints are done by humans unconsciously. So we want to detect this kind of space. One example is when you are looking at an exhibition. You are going to have a space between you and the exhibition, and you're paying attention. But also your body is going to be oriented towards it. In here, for example, the lady that is in the right side is taking a picture, but she is not invading the space that is already physically occupied, because socially we know that it's not correct to go between these spaces. So if we want to know more about how to detect these spaces, why should we track if we are interested in detecting human behavior? But why should we track this kind of things? For example, in my research, I like to talk about this topic because I want to improve the design for services that we can offer to other societies. For example, in the design of a train station, or in a mall center, or in a store. Everything that is placed because of a reason. And the arrangement of these elements are in front of your interaction with it. So you can pay more attention to it, and be more attracted to it. But also, modeling human behavior and how you interact with things and with people is important for robots. Because robots need to learn these models, these social models, and with that information, they are going to be able to interact with us more naturally. So how can we detect human behavior automatically? Because if we do that slowly and manually, that is not going to give us very fast results. But if we want to do that, which kind of data should we track? When we are walking, we have individual positions. So when we have in a tracker, we know where are you. But if you are walking with someone for a period of time, in a space of time, these positions are going to become trajectories. And with these trajectories, we can know where you were and to where are you going to go if we use an algorithm to do prediction. As well, when you stop, we can determine what is your focus of attention. And with that, the orientation of your body and what are you looking at. That came us to the social signals theory that's going to tell us that to analyze groups and the interactions, we need to have different aspects, like the space and environment, the distance that we have, that is called proxemics, this very nice distance that we have for 1.2 meters since Corona, that we are more aware of that. That comes from psychology theory. That's our model that have been developed for many years. Also, we have the arrangement, if we are seated or we are standing. We have the face analysis behavior, that is the gaze, what are you looking at, and the gesture and posture, that is going to tell us the body orientation. And how can we extract this data? There are intrusive body trackers, the ones that you place in your body or maybe in your pocket when you are in a place, and that is going to be calculating your position and your data. So that's one way. But the problem with these kind of trackers is that people are going to be aware that they're being tracked, so their behavior is not that natural. Also, we have manual observation. Someone in a place is going to take notes of how you move or what are you doing. But also, when you connect to Wi-Fi or you have your Bluetooth on, it's easier to have some kind of sensors in the room and start tracking your movement and which people are together and so on and so forth. But we don't want that. We want no manual observation because we don't have the human resources to do that. We want a simple design and setup because we don't want to have the room full of sensors. Also, we want it unobtrusive because we want a natural human behavior. We want to know that really how people are behaving without any intervention. And also, we want identity safe. Yes, we know and we want to track how are you behaving, but not to harm you specifically. It's to use that data to create better environments for you to interact better with everything that is around you. So when we do that, there is a kind of data that is called skeleton data. And with the skeleton data, we are having a model of how is your body. Think about it as a stigma. So we are going to have joints that are going to be your head, your shoulders, your knees, and so on. And everything is going to be connected. And then we are going to have this kind of stigma. When we have a sensor, we are going to be detecting these kind of skeletons, and with computer vision, we're going to extract this skeleton. And that can be every 0.2 seconds. We can have any time stamp that we want. But which technology is going to help us to do this? With RGB cameras, there is a library called OpenPose, so maybe some of you have heard about it. It's working computer vision using RGB cameras. There's also a Python implementation for it, and we can have this nice kind of animation that we're going to have the skeletons. But the problem with this, or more likely the limitation with these kind of things, is that we need RGB, so we can easily identify people. And also, we cannot see, for example, the person that is in the window. We cannot know how far he is from the scene. How high, for example, are the people that are dancing in the table. We cannot know that. We only know the position of the skeleton at that point. So the thing that's going to help us to do that are stereotype cameras. And there are many models and different technologies that are going to help us to extract the data. But today we're going to talk about the stereo vision cameras. And in particular, we are talking about Zed2i, that is the one that I have right here, and we're going to play there with it. And this stereo camera works exactly like your eyes. We're going to have one image in each eye. And how our bodies detect what is far and what is close is that it's going to calculate the difference on each one of the images that is projected in each one of your eyes. And that is how we perceive them. And through mathematics, we can know how far are objects from us. Of course, there are some limitations according to the range. This is only working for 20 meters or so. The scalability can be medium because we need, of course, the cameras and equipment for doing this. And also, we need certain light conditions to make it work properly. And we can make it work properly. We are going to have better tools to do exploration and measurements, so we can put the camera in a robot or something that is exploring the environment and have this. And on the right side, you're going to be seeing the depth model. So the darker the color, the farther away, the lighter the color is going to be closer, and that's going to help us with augmented reality. And once we have this data and we extract the skeletons, we know the locations, but here in the smallest one, you can see that we cannot detect who is specifically each one of these persons. But we can identify each one of the bodies. So we give each body an identifier, and with this identifier, we can know who was the most active player, or who was the most active person that was talking, and so on. So how do we play with this kind of technology? If we have a set camera, we can use PyCon. PyCon is the specific library that is developed by Sosa-León to work with this camera. There are the tail steps. We're using this in the GitHub repository, and the Steering Lab documentation, and at the end of the presentation, we're going to have a QR code to open it and get it to the corresponding links. So the camera requirements, of course, because we are doing computer vision, we are going to need a good computer with graphics card, preferably a GTX 1060 or higher. It's very important to have 3.0 USB port or higher to get able to get on data, and a good RAM, and so on and so forth. This camera works in Windows and in Linux as well, so you can use any operating system. So when you set up the camera, you're going to go to the Sosa-León webpage. You can download the SDK, the software development kit, at the latest version. Right now it's at 3.7. And you are going to be taken into the Qt app or NVIDIA to download the corresponding installers as well, because we are going to need that. Once you have that, you are going to review the camera setup, and we're going to have the diagnosis of the camera. And you can see here that we also have artificial intelligence models that are going to optimize how are you looking and how you are generating those skeletons. In the right side, you are able to see the RGB image that is the one that is taking the camera. And on the lower left side, you are going to see the depth map. Remember, the lighter the color, the closer it is. And when we have this kind of information, we can recreate a point cloud with everything taken into account these distances, and we can be able to see it everything. When you are setting up your development environment, you are going to have two options. You can do the manual install, that is in the main directory, in the root directory. You are going to have a file called get python./API.py, and it's going to finish installing all the libraries and all the corresponding dependencies that you're going to use. You can do that from the console. But if you're not so familiar with the console, you can also go to your Anaconda navigator, create an environment specifically for the camera, and start installing the Python library from there. So if we go to the Python implementation, we are going to be able to go to the repository, and there is one that is called set examples, and we're going to have several examples to start working right away. And when we do that, we're going to have the SDK library, that is the one that we just installed, that is the import python.lsl. We're going to move the camera, we're going to have different coordinate systems, because the camera can have different orientations. And different orientations means that your coordinates can have different values, so you need to be careful with that. Also, at the end, you're going to select your skeleton data format. And this skeleton data format can be 1836 or 48. What does that mean? That you're going to have more details of those stigmas. So you are going to have a very simple map with just the wrists and the elbows and so on. One with very detailed faces, like where are the ears, where are the eyes, and so on and so forth. Once you have the data, you are going to have a join key and a coordinates. You're going to retrieve that object of each one of the skeletons. And when you do that, you access on each one of the keys. And remember, a join key is going to correspond to one of these nodes. And those nodes are the ones that are going to show you the value of the depth. And that depth is in meters, according to the origin of the camera. So we can do right away a test. I'm going to be using the set camera here. So don't be scared. I'm not going to record anyone. So don't worry. have the source code, and when we play it properly, the camera will start. And I have to put everything. So in here, this is the scene. Don't worry, no one is being recorded. It's just for now. So if I put the camera in front of you, maybe we're going to start seeing some skeletons, right? So there's people seated and so on and so forth. So, but if we don't want this RGB information, we can move here, and in here you see that we can check only the skeletons. I need to put better the camera. So we are going to see that someone is like moving the legs or something like that. He's here. Hi, something like. So we are going to see different skeletons. Why there are not so many skeletons? Because of the light, because the environment has some reflections, and because of the reflections, it can be affecting how the camera is processing everything. Also, a seated position is very hard to compute. So that's why there are not all the skeletons detected. And another challenge, of course, are the face masks. If you cannot have the face, then that's going to be a challenge. So that's one example. The slide come back. Perfect. So here's an example, in case it wasn't so clear, in which the body is moving and we're having the RGB video in this case, and you see that it's checking all the joints and everything every moment. But then, for which kind of applications can we use this, right? For what has been being useful. For example, in my research, I'm using these kind of applications to detect social groups. A social group is, for example, when one or two people, when two or more people are together in the same place and they are looking at the same thing, or they are having the same focus of attention. When we have this situation, for example, with the code, the source code that I show you, I extract all the skeleton data, and from what skeleton data I create the JSON files. When I create the JSON files, as you know, we can import it directly to Python and start processing this data with matplotlib, with Seaborn, and so on and so forth. So once we process those JSON files, extract the skeletons, and extract the relevant data, for example, in my research, I use only the upper body because previous research has said that the upper body is the one that is more relevant to detecting if you are being socially aware or not. So when we do that, we evaluate if you are detecting the face, because we are going to know more likely that if your face is there, it's a frontal orientation, and if your face is not there, then most likely you're giving your back. And when we do that, we have a threshold to correct the body orientation. And for example, in the upper part, you can see that this is only the skeleton joint. It's not people, it's just the coordinates, just numbers in an array. So when we take this data and we plot them in matplotlib, for example, or in Seaborn, we are going to be able to see how the body was moving. So we have the right shoulder and the left shoulder, and with those we are going to create a line that's going to tell us the shoulder line, and we can see how the body was moving through time. And also, when we see this a lot of points in which they are like very concentrated here. Oops, sorry. Here, when they are very concentrated, with a lot of concentrated points, that means that that person was stopping there for a very long time. So that's going to tell us, okay, this person was stopping there. And we can say, okay, if it's more than 5 seconds, they are doing something there, right? And according to some psychologists and some sociologists, when you are interacting, you are gazing for 3 seconds. So when you stop 3 seconds, 1, 2, 3, you are looking at something, and when you move, that means that that didn't catch your entire attention. And if you stay more than 5 seconds, you are paying attention to that. And in that way, you can exploit that data, like to what the user was paying attention. And we should make it like better, because users stop also something very interesting here is that we can see how the body is moving, like when you rotate, there is always a point in which you are rotating more or less. So that is something that we can also detect, like how people are moving their bodies. This is also, this kind of data is used in medicine for therapies for people, when people have difficulties in rehabilitation. This kind of information is also being used. Here we can see an example of how much is accurate this information. So in the right side we have a frontal diagonal orientation where we try always to have the same orientation. And on the other side we have a side orientation. And in this way we are going to evaluate if this information is actually relevant and how much in the camera field of view is working. And we can see, for example, the triangle that is very light in this presentation here because of the light. That's the field of view, because this camera is a cone and it is not completely a rectangle. So if the data, the people are outside the area, we cannot detect how are they moving. So that's also something that you need to take into account when you are designing your space. Then we are using this kind of data to create a group detection algorithm. And this group detection algorithm is going to tell us exactly where the people were stopping and with how many people were in that group. So we will evaluate the engaged attention, so it's going to be called the stop. We use we create this with a machine learning algorithm, with a supervised algorithm that's going to tell us the number of people that we are expecting in that group and where are they located. So we evaluate how proximity is working. According to health proximity, we as humans have a personal space and a social space, and our maximum social space is 1.2 meters. So that in Corona times, people were 1.2 meters was not random. It was not a random number. It was sociology for the 60s that already told us that that's the number. So we evaluate if we are doing that. We assign the groups for all the people that are in those kind of spaces. We calculate the field of view. That is how much is your body and your attention extended. And if everything intersects and if everything goes at the same time, spatio-temporally, it's okay, then that means that you are participating in a conversation with that person. And most likely you are having a focus of attention. We can, for example, when we have a room and we locate the positions of exhibitions or products, for example, when we are in a mall or something like that, then we can see which products, for example, were the ones who got the more attention and exploit those products, for example, create better exhibitions for those. Or for example, when we are in museums, which exhibitions are having the most attention. Then we can create a polygon that the group space. In sociology, we have that there are this invisible space, that the inner one is going to be the most intrinsic and the most valuable in the social interaction. But we also have an invisible space around us, that is the one that I'm interested in my research and that I'm working on in the future year, in the next year. So, but the first approximation of my research, 90% of the time, it was this information was very useful to accurately detect these groups through any interaction. In the case of the Zed camera, if you are more interested in this kind of research, there is a paper that is evaluating not only the stereo camera, but also the Azure camera that you might have heard. Also the Kinet camera can also detect these skeletons, so we can also extract data with them, but they need to be handled with C#. So that's another kind of coding. So now we can talk about the challenges. So there are what I call the two main challenges when we use this kind of technology. The first one is the social one, because we have cultural context. It's true that according to the culture, we're going to have different distance, we're going to have different approximations to people, and even different arrangements. In some societies, the leader has more distance to others, whereas in other societies, they are more central, right? That is one of the challenges. How can we create a model that is capable of describing all these situations and making it reproducible in different kinds of research, especially right now in robotics? Also the privacy concerns. Despite having only skeleton data, people are still concerned that this kind of data can identify them. But we need to educate people that this kind of data offers a certain level of privacy that cannot be achieved, for example, with RGB cameras. Also, bias in algorithms. At the very beginning, when there were skeleton data algorithms created from RGB cameras, we had training algorithms. So people from specific developers, specific cultures and regions were training the algorithm to detect the skeleton. So at the beginning, we have like very tall people, or only guys, or only girls. So nowadays, the improvement of these algorithms in detecting and reproducing this skeleton data is getting better because we have now better technology and better techniques and more knowledge about it. We can start using more neural networks and be less dependent of training, doing the training data. And then, of course, we have the technical issue. Because these kind of technologies can consume a lot of computational power. They need always a good computer, and they also need a good graphic card. And for those who remember, the last 2 years was very hard to get a graphic card. The crypto market was extreme, and it was very difficult to get those kind of technologies. And even in research, it was very hard to try to get this technology to work on these projects. Also, we have environmental factors, and not only the ones from the crypto, but more the ones that we have here, the problem that there are reflective surfaces, that the light can be an inconvenience. Right now, the face mask can be a very, very challenging. But currently in research, ironically, thanks to Corona, we are starting to create more independent algorithms from the face, because in a lot of cases, we cannot have the face. That's true. Especially if you want to keep the privacy, right? And also the setup configuration and placement. Like in here, looks a little bit sneaky, the camera, but anyways, people knew that there was here a camera. So how can we place and configure this environment with these cameras so people can behave naturally, so people feel comfortable? Because not everyone will feel comfortable with this kind of technology. But all these challenges are just things that we're going to be able to come with a solution pretty much in research and also in the development environment, because they're very important for all the services that we want to use in all the situations that we talked about. Also, it's going to help us to design better the places that we explore, and hopefully in the future we can give good models to artificial agents that we create to have a better approach to humans, and to create better environments and better services for everyone. Thank you for your attention.
Thank you very much for your presentation. So we have some questions on Slido. So I'll just read those off to you. So first question, can the camera detect players in a soccer field? Can the camera detect players in a soccer field?
I cannot hear you properly. What? Yes, it can. Like we saw for yes, it can. But for example, in this particular camera, it's going to be a range of 20 meters maximum. This kind of camera. For example, the Azure camera can have 10 meters, but it can be more precise. So because the Azure is not going to have the confusion of the color as the stereo vision has, so that would be a better approach to use a laser camera as the Azure camera. But yes, of course, it can be done, as we saw that they were playing basketball as well. But yeah.
So the next question, what conditions make correct detection harder or easier? For example, you mentioned positions sitting, face masks, and light conditions. And for example, is clothing relevant?
Okay. Yeah, great question. As I mentioned, face masks can be a challenge, for example, for RGB cameras. Other cameras that try through the stereo vision can handle that better. So face masks, for example, we have different colors. That also goes with the clothing colors. So if we have like a lot of people dressed in the same way, like merged, like overlapping, that can be a challenge. So the software, the algorithm will have to discern better this kind. It's going to be harder, but it can be done in this particular camera distribution.
So then there's one more question. Can individuals be identified from gait analysis or other patterns of movement?
Yes, they can. For example, if we have spatial temporal analysis that is replace cameras and we know the time in which the body was there, we can have the person that was moving around, like a specific. So we know that those specific coordinates have been moving in the space for a period of time. So that can be a way of identifying individuals. But for example, if by identifying you mean the name, no, I don't think so. But yes, can be the gender, for example, if it's tall or if it's smaller. There are some patterns in gender that will tell us if they are more tend to be a female or a male. Yeah, so it's more about demographics more than identification specifically.
There's one more question that just came in. Can we use this application for security, for example, detecting a dangerous person?
Yeah, I would love to have this technology applied to that, and actually surveillance is working on that. Because if we can analyze someone that has a pattern in the movement that is suspicious, like getting too close to people, or moving too fast, or changing too much how it's moving, then we can say, okay, this body is moving or behaving irregularly. Like people usually don't move too much and stay too close to someone. So yeah, hopefully this can be one of the applications of this kind of technology.
So it looks like there are no more questions at the moment, so we'll end the presentation here. Thank you very much for your talk. Everybody, please give a big round of applause to Nicoletta.